Here we go. I didn't hear it. What? Section 2.1. Because we like to go in order in Algebra 2 class, we just left Chapter 11 to come back to Chapter 2. Section 2.1, folks, has to do with relations and functions. We're getting ready to, bless you, it's just some strange stuff. It's all good, though. Please stop talking while I'm talking. Here we go, relation. A relation is a set of ordered pairs. Set of ordered pairs. And folks, from, an ordered pair, of course, is this. And if it's a set, it has to be in the fancy brackets. No, you could have a set of ordered pairs. From those ordered pairs, folks, we have the domain and range. This should kind of be a little review from Algebra 1. The domain, those are the values. Well, actually the x values. From the ordered pairs. And the range, of course, if the domain, if those are the x values, then the range is the y values. Okay. If a relation is a function, then this means that all of the x coordinates, if a relation is a function, then all of the x coordinates will be different. And that's just to review a little bit from Algebra 1, okay? Bless you. We're going to be looking at a few different things dealing with domain and range. This is when you truly have to be a forest person. Kind of have to step back and look at graphs and from a forest perspective. You'll see what I mean in just a little bit, okay? But before we get to the actual coordinate plane graphs, we've got to be able to determine from a set of ordered pairs, from a mapping, from a table, what the domain and the range values are. And it's very simple, very simple. Everybody have this? All right, let's look at another. Let's look at a mapping. A mapping is a way that we can represent a relation, okay? Does anybody remember what a mapping is? Do you remember what it looks like? It's two ovals, one representing the x values, one representing the y values. And it could have, however many numbers in there. Do y'all remember those? Yeah? You briefly go over them in Algebra 1. That's called a mapping. It's just those two ovals. Of course, the domain for that relation is what, folks? The domain would be what? 5, 3, and 1. The range would be what? -2, 4, and 7. Correct? It's pretty simple to figure out what the domain and the range is from a mapping. You might also have an XY table. And we've dealt with these. We definitely dealt with these in probably Math 6, 7, maybe Algebra 1 a little bit. That's another way that you can see a relation is in an XY table. Domain is what from that, folks? -3, 2, 5. The range is 0, 1, and 6. I'm not even going to write it down because that's, it's set up domain and range. How about this? How about if you had a coordinate plane? Okay. What if you were given a coordinate plane and you were told to list the values of the domain and list the values of the range? Do that for me now, please. What are those values of the domain? Adrian, what'd you get for that? The domain. 1, 5, and -2. Is it okay that they're not in order? Sure, it's fine. Totally fine. What would the range be then, India? 2, -1. Now, didn't mean to do that. Did not mean to do that. Have those two same values. Should I put both those values twice? I don't have to put both those values twice, okay? You're right in saying that, hey, there are two values, but when it's the same value within either the domain or the range, you only need to list it once, okay? So just close it up after that -1. Now, this is kind of cool. Didn't mean to do this. Is that a function? That's a relation that you're seeing, okay? Is that a function? Why? Because my x values don't repeat. Is it okay that my y values do? Absolutely, that's completely fine. But this is a function. Completely is a function. What if we extended the coordinate plane and we started looking at graphs of lines, graphs of whatever, curves? When we're looking at graphs, folks, we can use something, it's just like a helpful tool called the vertical line test. Do you guys remember that? The vertical line test allows us, helps us to determine and look at the way I'm wording this, whether a curve is a function or not. Because I use curve loosely because some of these curves could be a straight line, but some of them are straight up curvy. All right, and you'll see what I'm talking about here in just a second. So using the vertical line test, what's the rule? How do we use it? What's the rule of thumb when we use that? What's that mean, Q? What's that mean? Vertical line, yes. We're going to draw a vertical line. Through the curve. And if that vertical line only passes through the curve at one spot, with each vertical line you draw, then it will be a function. Now, how are we going to word that nicely? Draw a vertical line through the curve, and if the vertical line doesn't cross our curve more than once, it is a function. And if you're like me, that's words. Ooh, show me what it means. Show me what that means. What does that mean? I need to see it. Let's say that I have this red line, okay? And that's my curve, quote unquote. Not very curvy. I'm still call it a curve. If I draw a vertical line anywhere on my line, it crosses it once. Crosses it once if I draw it here. Because, you know, I could draw a vertical line in one spot, and if you're down working on your notes, you might draw your vertical line in a totally different spot, right? So this is like my vertical line. This is like Catherine's vertical line, Nathan's vertical line, India's vertical line. Anywhere we draw a vertical line, if it only crosses that function in one spot, is that red curve a function, yes or no? Yes, it is a function. Let's look at another one. Hey, what have we been in? Speaking of curves, haven't we been dealing in the land of parabolas, quadratics lately, right? So if I were to draw a parabola, is a parabola a function, folks? Even without drawing a line, what are you thinking, yes or no? Yeah, all right, so let's draw a line. Okay, so here's Jessica's line. Crosses once. Here's Christian's line. It only crosses once. Here's Q's line. It only crosses once. Hey, are we safe to say what? This parabola is a function, right? Is a function. All right, that makes sense. What would be some pictures that wouldn't be a function that I could test with the vertical line test? Anna? A circle. Huh. Examples of non-functions. Tested with the vertical line test. Anna says a circle. All right, so draw a circle. I don't know. Let's say that I'm drawing my circle and I decide to put my vertical line right here on the side. Well, it only crosses at one time, right? So that means it's a function, right? Why not Mariah? Because Mariah says, oh, I'm not putting my line right there. I'm going to put my line right here. Up. This is when you should hear the bullhorn. Wah, the foghorn, whatever you call it. What's it going to be right there, folks? How many times does it cross? Twice. Is a circle a function? All right, you ready? Here we go. Examples of non-functions. Any closed shape. So I could draw a triangle up there. I could draw a rectangle, and they would not be functions, correct? Okay. That's a good way to describe it, too. A heart, which is actually called, if we took it to that point in trig, if I could ever get there, a heart is an actual shape that we could go over in trig. It's called a cardioid, I think is what it's called. But it is the shape of a heart. Let's back up, though, from shapes. What kind of curves? A sideways parabola. Because there are such things, folks, as sideways parabolas. If I drew, now again, same thing could happen. I could draw my vertical line right there at what we, bless you, would think that was the minimum point. Now we know it's not the minimum point as we learn in, but if I draw another vertical line, 1, 2, it crosses twice, which means not a function. Give me another example. A circle is not a function, right? Because it crosses twice. The sideways parabola is not a function. A straight line, what kind? Because this kind of straight line, a horizontal line is a function. Would you agree? A vertical line, though, is not a function. A horizontal line is. Put it in its own little box. Horizontal line is a function, but a vertical line, nope, not a function. Well, holy moly. I mean, I could draw a straight line right on top of a vertical line. Vertical lines are not. What would the name of that equation be? What would I call it? Like, usually our equations would be y equals 2x plus 4. What would that equation? Because it can pass through the origin. Anybody remember look right here. Let's see if I can make this where you can see it. X equals 2. That's the name of that line. Okay? I want you to know what that is if I were to give you just the equation versus just the picture. Courtney. Uh-huh. All right, then it would pass more than one spot. But no, remember now, a parabola is going to go out every single time. If you were to look at the table of values on a parabola, as the x increase, like saying it's an open, upward-facing parabola, right? I feel like I'm talking about yoga. If it's like this, if you look at the table of values, then as x increases, so does y. Even if it's just a little minute piece, it's still increasing every time. Okay? Questions on this? We could also have a sideways absolute value. Okay? That's clearly not a function. If I can draw any vertical line on the graph, and it crosses it 2 or more times, it's not a function. Okay? Just out of curiosity, what if it were a polynomial function? And it looked like this. It is a function, right? Because I can draw any vertical line through that polynomial function, and it's going to only cross it one time, right? Just something to think about. If we drew it like a S, then of course it would not be. You get the point of the vertical line test. It's just a real helpful tool, very helpful if you're looking at a picture, correct? All right, let's take it a step farther. Ooh, what about this one? Y'all know, because y'all always bust me on special cases. There's something called step functions. AKA greatest integer function. We haven't really talked about these ever a lot until this class, and we're going to talk about these a little bit later, but I at least want you to know what they look like. A step function literally looks like steps, okay? Watch this. I mean, they look like horizontal steps. Sometimes they'll have closed circles on the ends. And remember, what do closed circles mean? That those values are included. Now we're not talking about, you're right, it's in geometry it would be a segment. But for algebra, a closed circle means that value is included, correct? So if I were to draw a step function, is this a function? If I draw a vertical line, it only passes through one time, doesn't it? Is that a function? Yes or no? Yeah? Okay, that's a function. But what about this? Let's say this one only has two. Now look very closely how I have that drawn. What are you thinking, Dante? Not a function. Why? What's the kicker? Because I could draw that vertical line, folks, and that x value is going to be the same, okay? Because it's crossing that function two times. So this is an example where a step function is not a function. And why do we call it a step function if it's not a function, right? It'd be just a step. Very good. One more. Here's the weird part. What if I had that same picture? But I had open circles. What do the open circles mean? That those values are not included. So, this one would be a function because, all right, it is a function. Let me move that up so you can see it. Why is it a function? Because of the open circles. Those values are not included. That's supposed to be an F. That's just some weird stuff, okay? Step functions are just strange. Very, very odd. What are you thinking? Facile, difficile? Facile. Vertical line test is easy. Draw a vertical line. Okay. Do it. It's very, very easy. Now, that step function, though, thing, that's kind of got a twist to it. You got to be mindful of the open versus closed circles. Now, what about determining the domain and range. Let's take this one step farther. We're going to look at the domain and range tomorrow specifically. Let's look at these function notations. I'm going to give you all kinds of crazy graphs tomorrow. And we are going to determine the domain and range from those crazy graphs. Okay, we've got to look at the width of the graph, and we have to look at the height of the graph. The width of the graph is going to represent what? I'm giving you the trailer to the movie. Here's your trailer to the movie, right? Y'all know this is the commercial you see that's advertising the movie. Here's your trailer. Okay? The domain is the width or the height of the graph. Why is it the width? Because that's where your x-axis is. So then the range will be the what of the graph? The height. Now, that's your trailer for the movie. You got to be here. All you little field trip people, you're going to miss the movie tomorrow because we're literally going to watch a movie. Sucks for you. Notation, here we go. No, we're seriously not going to watch a movie, you know that. Function notation, I just fooled you. Ha 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 ha. No, nothing down by the river. Here we go. Folks, function notation is when it is. Yes, ma'am. Y equals blah, 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 blah. Okay? The f of x, g of x is going to take the place of the y. Now, if I gave you an example that said, yeah, dot, dot, dot. Yeah, it's going to be f of x equals, or g of x equals, okay? That's the same thing as y equals. If g of x equals the absolute value of 2x minus 3, I want you to find g of negative 1. Oh my goodness gracious. This looks like it's crazy, but this is so easy. What property are we going to use? All we're doing is substituting, folks. All I'm doing is I'm substituting negative 1 in place of what? X. That's all. Dante, that's all. Substitute negative 1 for x. So I'm literally going to rewrite g of negative 1, because that's what I'm finding, is equal to the absolute value of 2 times negative 1 minus 3. And I'm going to close the absolute value. Folks, find out that value for me, please. Did you get the absolute value of negative 5? Which is plain old 5. Because that's the value I am substituting. I'm putting that value into my, anywhere I see an x, I'm putting negative 1. Kinda. But it's literally just substitution property. That's all. Is this facile or difficile? Facile. Right? Take a quiz on this. Here we go. You ready? Here's another one. How about this one? It may be worded given f of x equals x cubed minus 3. Find f of negative 2. Don't you make a careless mistake. Plug it in, substitute. So I'm given f of negative 2 raised to the third power minus 3, right? What's negative 2 raised to the third power? Negative 8. minus 3, which is negative 11. Questions? Hey, what would the resulting ordered pair be from this? Just a forward-thinking question. What would the resulting ordered pair be from f of negative 2? Attaboy. Which takes the place of f of x, right? Very good. That would be the resulting ordered pair. Just saying. Hey, how about this one? Because this is so easy. It's substitution, right? It's just evaluating. What about this one, though? All right, you bunch of smarty McFarties. I want you to find f of the quantity b plus 3 when f of b equals b squared minus 6. Let's see what you can do with that. Don't you cut those eyes at me. Oh, take the b plus 3 and put it in place of b, correct? Okay. Let's just rewrite it. That's what you just did earlier. You said put the b plus 3 in place of b. Did I do that? Yeah. Now you've got the quantity b plus 3, quantity squared, minus 6. Evaluate that for me. Now, there's a reason I gave you this, okay? Yeah, this would be one of the most difficult ones, but it's not difficult because I have something squared, right? So don't I have to take that something and write it how? Say it again. I have to separate. How? What do you mean? The two quantities. Is that what you want? Is that what you were saying? So can I take the quantity b plus 3 times the quantity b plus 3 minus 6? Because if I were writing out everything in exponential notation from exponents to standard, don't I write that quantity twice? And of course, if it were a 3 as the exponent, then we would write the quantity 3 times, and that would be cruel of Miss Perry to do that, wouldn't it? So what are we going to do here, y'all? What are we going to do with this right here? Are we going to FOIL it out? That's what we're going to do. We're going to FOIL it out. So b times b, b squared. b times 3, 3b. 3 times b is 3b. 3 times 3 is 9. Minus 6. Now what? Combine like terms. We got 2 in the middle, and we got 2 on the end. Shouldn't we have b squared plus 6b plus 3, folks? How many of you had that? Very good. Very good. That's it. That's all we can do. That means that f of b plus 3 is the trinomial b squared plus 6b plus 3. Plus 3. Why? Because 9 minus 6 is positive 3, right? Did you like that? See it again? Shuffling off to Buffalo. No, I'm not. I don't really know what I'm doing. Having fun. What do you think? Did I do it wrong? Okay. It's okay if I did. Just tell me later. Motivational speech. Why? Because I live in a van down by the river. Facile, difficile. That's not that difficult. That is motivational, Dante. Yes, it is. All right, here we go. No questions? Any questions at all? Workbooks. Look at there. Folks, I want you to do on page 13 in your workbook. If you look at the instructions at the top, it says state the domain and range of each relation, then determine whether each relation is a function. If it is a function, determine if it's one-to-one, on-to, both, or neither. That last sentence, mark out the last sentence. We don't care about that. One-to-one, on-to, both, or neither. We don't care about the last sentence. Same thing in the second set, 5 through 8. You're going to do 1 through 4. No last sentence. Okay, don't pay any attention to the last sentence. 5 through 8. I do want you to determine whether those represent a function or not. And you can tell that once you graph those points for 5 through 8, or you'll be able to draw a vertical line and see if the vertical line passes through both points, okay? Or 3 points or 4 points. Only figure out, like 1A, 1 and 2A. Does that make sense? Your directions, follow the first sentence, and then the first half of the second sentence. So where it says is one-to-one, on-to, both, or neither, then state whether it's discrete or continuous, mark all that out. They sure did. And then like 12, just do like 11 and 12. No? It's not the whole page. I can assign the whole page. Okay. That's what I thought. So do I, honey. Look at the clock. Trying to help you out today. Trying to help myself today. Okay? 5, 6, 7, 8, 11, 12. Oh, 11 problems. Yeah, we do have busy lives, don't we? Look at the clock. Don't roll your eyes. Yes, please do.